This is a presentation of the 19th Annual Colorado Snow and Avalanche Workshop, a program of the Colorado Avalanche Information Center, Friends of CAIC, and the National Avalanche Center, presented by Dinafit and Pomoka.
Hi everyone, my name is Alec van Herwijnen and I'm from the WSL Institute for Snow and Avalanche Research in Davos. I'm here to talk about my new hobby, hunting for whumpfs. Before I start talking about this, I'd like to acknowledge my co-authors, Basti, Janic, and Karl, who really helped on this wonderful field day. So what are whumpfs? Well, whumpfs are essentially avalanches that happen on low angle terrain. So you have everything you have in an avalanche. You have the initiation of a crack propagation across the slope. But because it's on low angle terrain, you don't have the snow slab sliding downhill. Here's another example of a whumpf where Karl here triggered the whumpf. So he was the trigger. The crack propagated from here across the slope. But because it's not very steep, it didn't slide. So we have a trigger point. We have a cracked area, but we don't have an avalanche. So why do we need to study whumpfs? Why are they interesting? Well, like avalanches, there are small whumpfs and large whumpfs. And if we study whumpfs, we might know a bit more what helps crack propagation, what snowpack properties are conducive to widespread crack propagation. And this will tell us something about the expected avalanche size. And a big advantage of not having an avalanche slide on you is that the probability of coming home after a day in the field is quite a bit bigger. So there has been some interest in whumpfs for about 20 years now. The first measurements were 20 years ago by Crane Johnson and Bruce Jameson in Canada, good whumpfing grounds. They actually measured the propagation speed of a whumpf on a flat meadow with geophones. And as far as I remember, the stories from Bruce, this was a frustrating endeavor where they, for days on end, they tried to position the geophones on the snow surface and tried to trigger whumpfs, and it never worked. And on the last day, they actually measured the propagation speed over a distance of about 8 to 12 meters, I think. Then during my PhD study in Canada, I also looked at whumpfs. We collected data at sites of whumpfs and tried to figure out what kind of snowpack conditions are favorable for whumpfs. And we figured out that they're fairly similar to snowpack conditions also favoring larger avalanches. Then in 2013, Ned Baer submitted an NSF proposal to study whumpfs. And at that point, he suggested to do this with wireless accelerometers. Unfortunately, this project was never funded, but the idea stuck in my head. Then in 2016, I had the opportunity to have somebody build wireless accelerometer boxes as part of a graduation project for an electrical engineer. So we ended up with the first prototype of a wireless accelerometer, which we tested on PSTs. It took us a little while to get these boxes working well, especially the time synchronization between the boxes was a big issue. And then finally, in 2019, we got our first good measurement, and Basti talks about this measurement in his talk. And then what I want to talk about is the 31st of January 2020 is when we had a really very interesting field day where we could measure numerous whumpfs with these boxes. So let's jump to the 31st of January. Where did we do our measurements? Here's an aerial view of the site. Here's a road that goes down to the SLF. The SLF is just down the road here, a couple of kilometers on the way. And this is the Fluela Creek. It's a fairly narrow valley. It's a cold place in winter. It hardly ever sees the sun. There's a creek passing through here. So it's a very good area for breeding surface whorl. And there's these little boxes here, which are all bunkers that belong to the SLF now. And this one over here is Karl's bunker. Karl will talk about some of the measurements we did there last winter as well. This one was Basti's bunker, and over here are the Whumpf measurements we did on the 15th of January, where Basti will talk about. And these little dots down here, close to the creek, those were the measurements on the 31st of January this year. So if we zoom into this area, it looks like this. Here you see the dots is where we had those little boxes, different Whumpfs. And we ended up measuring 8 different Whumpfs, crack propagation distances up to about 12 meters. And it really was one of the more unusual field days I've ever had. Now you might think, why are all these dots in the river? Is your GPS off? Actually, it's exactly what we did. We ended up measuring Whumpfs right in the river. There's all these little islands with snow on top, and on that day conditions were perfect for Whumpfing right in the river. So there was a little layer of surface hoar that we had been tracking for a while, and it finally got covered by snow. And on that day, it was very reactive. So I must say it's the only field day I've ever spent in the water. So it made for some interesting photos. All these little islands here, you can see this is a tiny little island we managed to Whumpf. There's another little island over there, a bigger one in here. Everything Whumpfed. And yeah, so we were wading around in the water and trying to Whumpf these little islands. And yeah, wading in the water, quite unusual if you're a snow scientist. It made for a fun day and also for very good measurements. So what did we measure? We had the accelerometers, which we throw on the snow surface. I'll talk about this a bit more afterwards. Then if we managed to trigger a Whumpf, we measured with the SMP to get snow stratigraphy. We also recorded a few manual profiles. And of course, we had to determine the position of all these boxes. Manual profiles, here's an idea of what the snow cover looked like on that day. A very thin snow cover. Here only 55 centimeters of snow. And most importantly, what I'm showing here is a snow depth and hardness. And the colors indicate grain type. Green colors are new snow, red is rounded grains, blue is facets, and these little pink lines are surface hoar. And this bottom layer of surface hoar was very reactive on this day. And you can see a little stripe here in the snow pit as well. So it was a fairly shallow slab, only about 30 centimeters and pretty soft, very reactive. We also have the SMP measurements to characterize the snow cover in more detail. And here is what it looks like when we plot it on top of the snow profile. So much more detailed data about stratigraphy. Most importantly are these accelerometers, which were developed at the SLF. So these are 3-axis accelerometers, so they measure the displacement in the acceleration in 3 different directions. Each box also has a GPS for time synchronization. It has a little battery in it, and there's internal storage where we can measure up to 6 hours per day. How does it work? What do we do with these little boxes? Well, this is what it looks like. Here we have Karl and Janic standing in the water at a safe distance. And here is Basti with his snowshoes. And we've placed a few boxes on the snow surface where these red dots are. And the idea is then to trigger a Whumpf, trigger a crack which propagates outwards, and these accelerometers will measure the settlement of due to weak layer collapse as the crack propagates. In practice, it looks like this. Here we have Basti walking up to the first box, hoping to Whumpf. If nothing happens, we pick it up, we throw it out, and we try to keep the accelerometers in one line. And we just do this all day long until we hope we get a Whumpf. In this case, nothing really happened. Here's another example where we tried this on a slope. Again, here are our little boxes. And this is Karl and Janic, again, being at a safe distance, and Basti will try to trigger a Whumpf. In this case, it was a bit more exciting. At the second step, you can see a little avalanche release, propagated outwards onto the cross-country run, and then broke off the cornice, and it triggered a little avalanche on this side. So very complex pattern of crack propagation. Luckily, we made this movie, so we know what happened. So what do we do with these little boxes? Like I said, they will measure the acceleration as the crack propagates and collapse as the weak layer collapses. So after a Whumpf, we had to measure the distance of each box relative to the trigger point. And then if you have distance and you have a signal, which looks like this, here I plotted the distance to the trigger point and the signals with time. And you can see that the first weak layer collapse wave passing at the first sensor. As you move further away, the signal comes a bit later. So you need to pick the onset time of these signals, then you have time and distance, and you can get propagation speed. So in this case, we get a bunch of different speed values with distance from the trigger point, and we can see for this particular Whumpf, speed increased as crack propagated further from the trigger point, up to about 12 meters. So here we have values from 5 to almost 35 meters per second, and on average, speed here is 8 meters per second. And like I said, we had 8 different Whumpfs. So if you put all the measurements together, we have here again crack speed with distance from the trigger, and the colors indicate the different Whumpf measurements. So it's a little bit all over the place. We have measurements ranging from 5 to about 35 meters per second. And here in the legend, I show the mean speed for each Whumpf, which ranges from 8 to 23 meters per second. And this was the first example I showed where we have this nice increase with distance from the trigger. But at the other Whumpfs, there was not really a trend, maybe sometimes a little decrease, or it was mostly flat. Now these light blue dots here, that was the avalanche where I showed the movie. The crack speeds here are not very different from the other Whumpfs, although it was in a 40-degree slope. And overall, we end up with a mean crack speed of 16 meters per second. So why are we interested in this crack speed? Well, first of all, it's relatively easy to measure. It's also something we can measure with a PST, as Basti shows in his talk. But also, there's the assumption that if cracks propagate faster, they will propagate further, so that crack speed will be indicative of avalanche size. Now the question is this really the case in snow or not? And there's not many measurements, direct measurements of crack speed. And here I've plotted all the measurements we have now. Blue shows the measurements from Crane Johnson, the Whumpf site in Canada, where they measured up to distances of about 15 to 17 meters, and a crack speed of 20 meters per second. I measured crack propagation speeds in 2011, this light blue dot, in an avalanche with seismic sensors. The avalanche was about 60 meters wide, and I measured a crack speed of 40 meters per second. And the measurements from Basti on the 15th of January, where we don't really know how big the Whumpf was, but we estimated it to be around 40 meters in size. And we had crack speeds around 50 meters per second. And these measurements from the 31st of January are the dark red dot here, where we had fairly short propagation distances and fairly low propagation speeds. So here, although it's only 4 data points, it does suggest that higher crack speeds correspond to wider propagation. So to sum up, this was really the first time I did a snow profile with my feet in the water, and it made for a very, very interesting field day. We measured propagation speeds at 7 whumps in one avalanche with speeds ranging from 80 to 23 meters per second. If we combine our measurements with those from others, we get the measurements suggest that propagation speed relates to propagation distance. But obviously more measurements are required. We only have those 4 data points, especially on steeper slopes. And maybe this will take another 10 years. It took us 20 years to get 4 data points. So who knows where we'll be in 10 years. Now, what's very interesting with these measurements, I also gave this movie to Ron. He has a talk where he looked at how you can extract crack speeds from videos of avalanches. And I gave him this movie because we obviously have these measurements from the acceleration measurements, and he can also extract crack speeds with his method, and we can then cross-validate both measurements. And obviously, such measurements are also very important for to validate numerical models where we can nowadays model the processes that happen in an avalanche at the slope scale, as you will see in Joan's talk. And with these measurements, we can actually compare them to what the models predict, and then hopefully confirm that what they measure is correct. So thanks for your attention, and I look forward to an interesting discussion.